Okay, so what's the function f doing? What does function f say to do? Square something and add 1. So if we were to square g of x and add 1, we would be squaring that entire function and adding 1. What happens next? X, the square root cancels, right? So it's x minus 1 plus 1. Do you see I get x? Okay. That is the definition of an inverse algebraically. I'm going to show you because I have always talked about how graphically to me things often make more sense. Let's go the other way. It has to work both ways. They have to be able to invert one another. So let's do g of f of x. So the function g takes the square root of something minus 1. So I'm going to take the square root of f of x and then subtract 1. So, what am I going to put there? X squared plus 1. X squared plus 1 minus 1, the plus 1 minus 1 cancels, right? So we're talking about the square root of x squared, which is just x. Okay. Okay, now, sometimes, I'm going to talk about this graphically because sometimes the entire function is not invertible, and this is, invertible means you can find an inverse. There are some things that you can't find inverses of. There are some things that are not undoable, I guess. Okay. Do you guys remember at the beginning I was saying when we squared 9, we got 81? So that would be the ordered pair 9, 81, right? I put in 9, I got out 81. But when I did the square root, I took the square root of 81 and I got out 9. Okay? And so what we need to understand is this inverse relationship. That if A comma B, you can't see? If A comma B is in a relation, why am I calling it a relation? It could be a function, but it could not, because we talked about how circles are relationships, but they're not functions. Okay. So this is just a general rule, because you can have inverse relations too. If A over B is in a relation, then B over A, or not B over A, B comma A is in its inverse. Okay. Chase, give me a number.
12.
12.
Oh, yes, I do.
So f of 12, would you find, what's f of 12 for me? Uh, 12 squared plus 1, okay. But then add the 1. Okay, so would you agree with me, f of 12 is 145. That's the ordered pair, 12, 145. What I'm saying is if something's an inverse, it would have to have the reversed point. Then 145 comma 12 would need to be a point in the inverse, is it?
Yes.
Put 145 in, subtract 1, you get 144, the square root of that, okay. So, describe what's happening here in general. What's in an ordered pair, what's happening with the x and the y? they're being switched. Would you agree X is getting interchanged with Y? Okay. You really want a mind blow? What's the line Y equals X look like? The line Y equals X would be 0, 0, right? 1, 1, what else would be on it? 2, 2, 3, 3, okay. Y equals X. If I am reversing the X and Y, what it looks like on a graph, and I hope this makes sense because I'm making Y equals X, is it's flipping it over this line. Okay? Let's take our other example. What was it? X squared plus 1?
Yeah.
Okay. X squared plus, wait, on the previous page?
Yeah.
Okay. Y equals X squared plus 1?
Yeah.
So that's a parabola that goes through 0, 1, agreed? So it looks like maybe this. Are you okay with that? Okay. What was the inverse function? Square root of X minus 1. That's a square root curve moved right 1, okay? Now cover up this part. Don't those graphs, these parts, look like they are, remember from geometry, just flipped over that line? However, what part is not flipped over? Yeah. And so the reason why is this, because we've talked about this, you can't take the square root of a negative number, right? What would happen is, if I graphed that down here, this part would no longer be a function, right? So we would say then we have inverse functions, but we could only do it for x squared plus 1 when x was greater than or equal to 0. Okay. Yeah. So sometimes if you restrict, sometimes something doesn't have a total inverse, but if you restrict the domain, it does. Okay. All right. So that's all we'll talk about